let's bring this back down to Earth for a second. And let's look at gravity on Earth, meaning near the Earth's surface. All right, so the gravity near the Earth's surface, I would say that Fg accelerates all objects at 9.81 meters per second squared, which you already know from the one of the earliest weeks of this course, is that everything falls at 9.81. So let's see how we get that from universal gravitation. So let's say here is the Earth, and here's the center of the Earth, and here is something that we want to calculate the gravitational force on, and it's near the surface. And it could be anywhere near the surface. It could be up here, it could be over here. So the force on this thing, we could draw like that, Fg. And we know the force on it is going to be what? We know universal gravitation is always true. Big G, m1, mass of the Earth, m2, mass of the thing, and r is the distance from the center to the center. Okay. So let's see, near the surface of the Earth. Let's see what will we plug into this equation. Let's see, G is just G, so that's universal. M1 is going to become the mass of the Earth. Okay. And the mass of the Earth is 6 times 10 to the 24 kilograms. The Earth is really big. Newsflash, the Earth is big. R, which is squared, of course, r is the separation. So technically r would be the radius of the Earth plus sort of how high the object is. Right? So if you're right on the Earth's surface, if the center of mass of this thing is right on the surface, then it would just be RE. But if you lift this thing up to some height h, then you'd say, well, it's RE plus whatever height you have. Right? So that would be what you would plug in for the r when you make it r squared. Well, let's see, what are those two numbers? The radius of the Earth is 6,370 kilometers. Really big. And h, typically, you know, if I'm holding something up in the air and release it, maybe 2 meters, right? So usually when we're doing these problems, as long as you stay pretty close to the surface of the Earth, you don't mess with this, right? That's not going to make a difference. That would make it 6370.002, which is not really worth even writing down. So pretty much you plug in mass of the Earth here and the radius of the Earth there. And then let's see what we would get. Then Fg would be 6.67 times 10 to the minus 11 is big G, and mass of the Earth is 6 times 10 to the 24, like that. And then this would be 6.37 times 10 to the 6 if we're doing everything in MKS units. So since I didn't write any units, you can assume I did this in MKS units. And all of that times m2, the mass of whatever little object you're holding to the surface of the Earth. Okay? That's the universal formula, but that's now also the one we know, F equals mg, because if you put all these together, you get 9.81 meters per second squared. So this is how you find that value. This is where that value little g comes from, is the Earth near its surface creates an acceleration 9.81 meters per second squared. If you wanted to call it a vector field, you would say it pulls everything down with an acceleration vector, 9.81 meters per second squared. If you wanted to figure out little g, or the acceleration that something falls on another planet, you would simply have to plug in a different mass and a different radius, and that would be the answer. That's all you would do. Different mass, different radius, new acceleration. That same acceleration would be applied to any mass. So let's think about the moon for a second, right? We know we have been to the moon, and we know that on the moon the acceleration due to gravity is lower, and we know that's because the moon is smaller. So if you look at this, you might say, well, oh, good Lord, I can't keep that too. If you look at this, you might say, well, if the radius is smaller, what does that do? Well, if the radius is smaller, it should actually be bigger, right? So smaller radius means you're closer to the center of mass of the planet, so this would make it go up. but the mass would also come down. But how much? Oh, well, if the moon is about the same density as the Earth, then the mass goes as the radius cubed, because it goes as the volume, right? So this goes as r cubed for any planet, and this goes as r squared. So if you have another planet with a similar rocky sort of density to ours, although density probably depends on size, you can see that it would go down as you get smaller. So it does make sense that the moon has lower gravity than we do. Okay, but that's the connection between universal and Earth surface.